this guide's going to take you through how to select your shaft diameter and your bearings. It's a bit more complicated than selecting the pulleys and the belts, so I thought I'd do one explaining how to do it as I go through it. So this is pretty much the drawing of all your reaction forces on your shaft and your bearings. You've got your complete, your full bearing reactions, which you'll be able to calculate later, and this is what you need for part of what's to be submitted. You've got your weight of your pulley, then you've also got your weight of your shaft, so you can't really calculate or find your bearings until you've done your shaft. It's kind of you got to do both at the same time kind of thing. So that's the reaction force is the thing, just to kind of explain where we've got to go with this. So first we have to find the shaft diameter and the weight of the shaft, which will then allow us to calculate what kind of reaction forces the pulleys have. The bearings are going to put on it, so we can find suitable bearings and then resize the shaft diameter to fit those bearings. So first we're going to start with moment diagrams of the shaft. We need them in two planes to find the critical moment from then which we can calculate our diameter. So you take two, one in the YZ plane, which will have forces of the weight of our pulley, mass mg, reaction force of bearings. Now obviously the shaft has been constrained to 1 meter in total. We can pick and choose where we want to place our bearings along that 1 meter. Important consideration is to put into consideration the bearing houses of which we're going to store your bearings in. You have to have enough clearance between your pulley and your bearing house and your bearing, so that your bearing house will fit in there. So at this stage you kind of just make up whatever you want. It doesn't really matter. It's gonna, obviously the different size lengths you choose are going to give you different results and allow you to choose different bearings and have different shaft diameters, different loads. It's completely entirely up to you. So for this example I've chosen 0.12 from either end to the center of the bearing, which leaves me with 0.76 in the center. The mass, I have been told, of the pulley, of the 630mm pitch pulley, is 220 kilograms. Times that by 9.81. To find the exact weight of your pulley, you can CAD it and then find the volume of it in your CAD drawing. Then multiply that by the density and that'll give you the weight of your pulley. So we need to calculate the reaction forces. So taking moments at point A gives me Now that we've calculated the reaction forces and we've drawn our moment diagram, we'll get our critical moment for in the YZ plane, which is, for me, is 258.984 Newton meters. Yours will be different, it'll be higher, lower, depending on the length chosen. I ask that you don't use the same as what I've got, just, you know, so that it doesn't look like we've all been copying each other. So once you've done that in the YZ plane, you then do it in the XZ plane. As you can see, I've drawn this one a bit bigger so it's easy to read. It's the same deal, except we replace the weight of the pulley with our static load, WS, which we calculated before doing our hub loads for our pulleys and belt section. You go through it again, you calculate your reaction forces. This time they're your bearing reactions in the X direction as opposed to the Y direction. These will come in handy later when we're calculating our bearing reactions. Then we draw the moment diagram again. In this direction, you should end up with a bigger critical moment, which is the moment we shall, or whichever one is bigger is the one you'll use to calculate your shaft diameter. But in theory, it should be in the XZ plane from your static hub load, should give you the biggest critical moment. I've got 560.08 Newton meters. Now we need to draw a torque diagram. If we remember, P equals torque multiplied by our rotational speed. For an RPM of 465.71, we get 465.71 divided by 60 times 2 pi equals 48.77 radians a second. Our power is 18.4 kilowatts. Remember, this is in kilowatts, not watts. Therefore, our torque equals 18,400 divided by 48.77 gives us a value of 377 Newton meters. Now our torque is constant throughout the whole shaft. There's a value of 377 Newton meters. So that makes this diagram easy. And our torque is also TQ for our next part. Okay, so next we need to come up with an estimate in diameter for our shaft. To get that, we need, it's called the trial shaft. And you will find the graph for that in your HB6 Appendix A, Figure A1. We'll also give you the following formula to calculate your equivalent torque. So TE is equal to 1.15 multiplied by MQ squared, which is our critical moment, plus 0.75 TQ, our torque that we calculated before, squared. So my values will give me TE equals 1.15 multiplied by 560.08 squared plus 0.75 times 377 squared. Returns me a value of 745.54 Newton meters. So following off the table here, using the high strength steel line, we have a value of 745, so that's 100, 120, 140, 160, 180, so we're in here. We follow that up to the line, bring that across, gives us a shaft diameter of about 25. I have 28 in my example that I've already done, so I'm just going to use that, but at least you know how to use the chart. So with 28 millimeters, now if you have the handout, this will help a lot. In fact, I think you actually need it. This handout here. Exercises on stress concentration and fatigue failure. On the back of this handout is a list of all the different a heap of different types of steel. I've selected my steel over here. It's kind of just pick and choose whatever you want kind of deal, really. You kind of know what stresses you should be expecting on it to resist from your moment diagrams. So you go through here, pick whatever you like. It'll tell you later whether it works or not. Things will work out or they won't. So that means you'll have to go back and choose a different steel if it's giving you problems. But I've chosen mine here. Mine has a tensile strength of 800 megapascals. So to get, then we choose, then on the page before that, from the same handout, we choose how we want our steel finished. I've chosen polished, which gives me an endurance, and then we've got to read the endurance strength off here, or megapascals on the right hand side, gives me an endurance strength of 400 megapascals. Then if we compute S-N, that'll give us our FR. So to find that, we have S-N is equal to 400, our endurance strength that we read off, multiplied by cm. It's all in this handout, all the things you need. This is a diagram for wrought steel, so our cm is 1, multiplied by our type of stress factor, 1 for bending stress or 0.8 for axial tension. There is no axial tension, so it's bending stress, so that's a 1, multiplied by our reliability factor. I've no idea what I'm supposed to have chosen here. I've just selected the highest value, which is 0.999. Gives me a CR of 0.75. Multiply that by the diameter. Now the diameter is in inches. You'll have to convert your 28 millimeters, whatever, into inches. 2.4 centimeters is an inch, which gave me 0.88. So my SN for my trial shaft is equal to 264 megapascals, which is also equal to my FR. So my FR is equal to 264. Then need my KS value, which you shall also find in the rotating shafts handout. KS is up the top here in this one. So for a shaft diameter of 28, that will return me a KS value of 1.25. And then finally I need my K value. The K value is a stress raising characteristic. Obviously we have bearings, so we're going to have to use figure 5 down the bottom of the page. You found your KS on, and then if you're putting keys in your shaft and your pulley, then you'll also need to use the one at the top over the page, figure 7. So using figure 5 with a tensile strength of 800 gives me a K value of 2.05. That one. And then over the page I get a 800, I get a 1.9. In HB6 on page, if I can find it, page 8, HB6, section 8.2, stress raising factor K. The value of the stress raising factor K shall be as follows. Now there's this A, B, C, and D here. You need to read all 4 of these and decide where your shaft fits into these. Just remember that these 0.25D or 0.16D, it's multiplied by the diameter of the shaft, not the length. But it's an axial distance, so don't get tripped up on that. Mine falls into B. which means I take the highest K value out of the two, so I'll be using K equals 2.05. Yours may be different depending on how far away you've set your bearings from your pulley. Because your pulley is where the key lies. So then we need to find our factor of safety, which is done by calculating how many stop starts there are in a year and how many revolutions there are a year. So the machines run for 14 hours, 6 days, 50 weeks a year. And it stop starts 7 times a day. My RPM is 465.71. So to get the number of our stop starts, stops 7 times a day for 6 days for 50 weeks. That gives me 2,100 stops a year. Now for the number of revolutions, it's 465.71 revolutions a minute times 60 minutes times 14 hours times 6 days times 50 weeks. Gives me 1.173 times 10 to the 8 revolutions a year. I then go to table 2 in the shaft section of my HB6, or in the handout. If I go back a page, first page after the questions, I'll have here. So my number of starts a year is greater than 600, and number of revolutions a year is greater than 900. So I want to use formula number 3. Which I believe everybody should be using. There shouldn't really be any reason why you wouldn't. And then down here at point number 5 will give me my FS value. The value of FS is 2.0 for Formula 1 and 1.2 for Formulas 2, 3 and 4. So my FS value is 1.2. FS equals 1.2. And that should give me everything I need to calculate my diameter. So using formula 3, which is diameter cubed is equal to 10 to the power of 4 times Fs divided by Fr times Ks times K times the square root of a critical moment plus this is axial load, we don't have that, so that is 0, plus 3/4 the torque squared. So putting in my numbers gives me 10 to the 4 times 1.2 divided by 264 multiplied by 1.25 multiplied by 2.05 multiplied by the square root of 560.08 squared plus 3/4 times 377 squared. Give me a number of 78,638.67. Take the cube root of that will give you your diameter, which for me is 42.8 4 millimeters. And that's just step one. You have to take a couple iterations of this, because obviously now that my shaft diameter has gone up, my KS value and also my FR are going to change. So I need to do a couple iterations of this formula. So you just find your new KS value, find your new FR value. Your FR value changes because your diameter has changed, so that gives you your CS value in your FR equation. So you just have to find your new CS, plug that into your FR equation, that'll give you your new FR. You just look up your new KS value, do a couple iterations of this. It will approach a number of its choosing. Once you've got a couple of numbers of this and it's not really moving, once you've done a couple of these, it's not really moving much and you're satisfied with where it's going, then you can move on to the next bit. So my second shot got me a diameter of 44.58 millimeters. The next one got me 45.16. Then my fourth go got me 45.3. Now there's a little bit of difference between there, so I was just going to stick with that. I wasn't going to go any higher, well, not significantly anyway. So now that we have the shaft diameter, we can calculate the weight of the shaft. Or actually, a better idea, I didn't do it this way in the first place, I probably should have, is to then go to your bearing catalogue, see what the next up bearing is from this. Obviously 45.3, I cannot go lower than that because I have a key in my shaft, so I have to take it up. The next stage up from 45 is 50, so my bearing diameter will be at least 50 millimeters. So to save me the trouble of having to do this, having to calculate the mass of my shaft over and over again, I'm just going to increase it to 50 millimeters right from the get-go and then calculate my mass, and that way I'll be able to get my bearing reaction forces for that weight, and it will tell me straight away whether these bearings are going to work or not. So with a shaft diameter of 50 millimeters and a length of a meter, the density of the steel being 7,860 kilograms per meter cubed, I'm then able to calculate the mass of my shaft. So with an area of 0.00785 meters cubed, I then multiply that by 7,860 to give me a weight of 61.732 kilos. So now I have the weight of my shaft and the diameter. I can then redo my reaction forces at the bearings to find whether my bearings fit or not. So in the YZ plane, draw my free body diagram or free line diagram. I have the mass of the pulley, the reaction of bearing A, the reaction of bearing B, the mass of my shaft, take my moments at A is equal to 2158.2 Now we only need to do this in the YZ plane because the mass of the shaft is now acting in the Y direction, because we now know that. We don't need to do the XZ plane again, but we will use the values that we calculated earlier from those to find the resultant bearing forces. So to find RAS, which is the reaction force of our bearing in static load. We take our values from our previous $37.97 squared plus this is, whoop, sorry, that's for B. 37.97 and 736.953 squared gives us 737.93 newtons. Our RA S is equal to square root of 2801.76 squared plus 5404 squared 2801.76 6087.41 newtons. So these are the reaction forces of our bearings at a static load. To find them at a dynamic load, we substitute WS for WR. Then we recalculate our reaction forces in the XZ plane, not the YZ. Then we just do this again and it'll give our dynamic forces. But from here we can then calculate our desired bearings, or whether the bearings we've chosen fit, work, won't break. So for bearing A, we have our P. Our P is just our bearing force, our bearing reaction force, 6087.41. We then calculate our life equation. L10 is equal to 40,000 hours times 60 times the RPM. Gives me 1.12 times 10 to the 9 revolutions. So C is equal to P L10 and 10 to the 6. Sub our values in. Will give us, to the power of K, that is. It'll give us C divided by 6087.41 to the power of K, which is 3 1/3 for roller bearings. Our L10 is 1.12 times 10 to the 9 divided by 10 to the power of 6. Returns me a value of 47019.21 newtons. So that's our C value for 90% reliability. We want 95% reliability. So obviously this will go up. So we get that by L5 is equal to 0.62 L10. You can simply multiply L10 by 0.62 and then do the equation again. Gives me a value of 54240.42 newtons. That's for bearing A. Bearing B, I've taken a shortcut, so I'm only really going to give you the answer for this one. B 737.93. Actually, I've just discovered these values are wrong because I've made a mistake throughout my calculations. The working's correct. Obviously, that's going to be 6087.41, and that's not right. But I'm just showing you how to do it. I'm not giving you the answers. So for bearing B at 95% reliability, it's giving me a value of 7,468.43 newtons. Obviously this is really low for the 50 millimeter diameter bearing, which even this is pretty low. This doesn't even really meet the expectations of the 30 mil bearing. So with this one here, you can step down your shaft to a smaller diameter for bearing B, which is on down the other end. I won't be. Won't be explaining why. You can figure that one out for yourself. And the solution to having such a huge life bearing as opposed to one that's not going to last quite as long as this one will if you put 250mm bearings on. Obviously they're going to wear at different paces, and so bearing B is going to outlast bearing A. Obviously if you're going to leave your shaft at the full 50mm the whole way along, you're obviously going to have to justify why you're going to accept a 50mm bearing for a load of 7,468 Newton meters. Yeah, and so that's how you select your bearings in your shaft. Obviously if one of these values exceeds the allowable of the bearing, your C for the bearing, you're going to have to step up your shaft diameter to accommodate a bearing that'll take the load. So then you'll go back and redo the calculations to find that, and that's pretty much it. If there's any questions, post them up on the EWB page or in the comment section where I've posted this video, and I'll do my best to answer them. Well, thanks and good luck.